Hello and welcome. This is AMAT362 Probability for Statistics at UAlbany. This is lecture 20. Today we're going to talk a little bit more about ways in which the CDF trick can allow you to identify the probability density function for a continuous random variable. We'll then end with this famous example of the rubber pencil. And hopefully I have a pencil nearby. All right, so this is more continuous random variables, where we illustrate the principle that if you differentiate the CDF, you get the PDF. And then today we'll talk about the rubber pencil as well. All right, so let's start with, again, one of the canonical examples of a continuous random variable. And this is namely the dartboard. As you all know, there's a bullseye, but let's not focus on how the dartboard is actually structured right now. And instead, let's just posit the following question, which is, suppose I can throw a dart uniformly at random at the board. How is the radial distance distributed? So we're going to call that, of course, little r. So to write down more precisely, the question is this. Suppose I throw a dart uniformly at random a dartboard. How is r, which is distance from the origin, distributed? And this is, again, as a random variable. So just as a quick recall, remember what this amounts to asking is providing a function that allows you to compute the following probability. So, all right, so here we're going to recall that the whole point of a continuous random variable is to be able to evaluate or find the probability that R lands in some region between A and B by evaluating some integral. R dr, for example. And this is what we're trying to find here. Which is the PDF. Now, we know how to answer this question already sort of intuitively. So intuitively, because I know that this is a uniform distribution, this can be identified as, let's say, I have A is here. That's my distance A. And I have B here. That the area of the strip between A and B that's the area we're trying to find. So we could think of this as the area of the strip. And this is as a relative of the area of the dartboard. Which we can write out an exact formula for as follows. it's going to look like, well, again, if you have pi times, your radius squared, I could take the difference of pi b squared minus pi a squared, and then divided by the radius of the dartboard squared, which we're going to assume is equal to 1, just for simplicity. So under that assumption, then, I know that this probability function, probability that A is between R and B, can be computed as, well, we have pi b squared minus pi a squared divided by pi 1 squared, which just ends equaling b squared minus a squared. Actually, from this, it's really easy to read off the CDF. So the CDF for big R, which we sometimes call big F, evaluated on some, let's just say evaluated at B, it's going to be the integral from, we can make it from 0 to B, because we know that there's no negative radius, there's no negative distance of whatever our PDF is, f of r, little r dr. And this in turn just equals the area of a disk of radius b. So now we're just asking, how does area grow as a function of the radius b? Well, to switch back to the notation we've been using, what this also implies, just by setting little r to equal b, there's no significance in this assignment, it's just a make notation match. We know that this is the same thing as the integral from 0 to r of some dummy variable, r prime, dr prime. It's just that we want to separate out, so we know that what we're integrating with respect to and what the limit of integration is are different. But by the fundamental theorem of calculus, we know that ddr of f of r is going to equal little f of r evaluated at r, which means that I can just plug in, well, we know what this is r squared. So ddr squared of r squared is 2r, and that is our PDF. Now, it's always nice to kind of graph these things to make sure we're understanding. So what this looks like is, obviously there's no probability density for a negative radius, but then probability density increases linearly up until 1, which we're assuming is the radius of the dartboard. But the slope of this function is 2r. So in fact, this ends up equaling r before then we have to drop back down to 0, because we're assuming we're not hitting anything outside the dartboard. So in fact, at this value here, we have 2. So this illustrates 2 facts. So nota bene, note well, that f of r at, let's say, 0.75 is 2 times 0.75, which is the same thing as 1.5, which is greater than 1. The upshot being that probability density can be greater than 1. And so again, this is meant to illustrate that probability density and probability are not the same thing. You have to integrate density to get probability. And you can integrate a function that's greater than 1 for a small window of values, and you'll get a number less than 1. which is necessary for it to be a probability. The other thing I want to note is that probability can be greater than 1. The second thing I want to note is that, at least in this example, we see how probability density concentrates around the perimeter. Which kind of makes sense because I don't know about you, but hitting right directly in the center, well, first of all, it's literally impossible. But hitting the bullseye, which is in a small region, the way you would find that is just by integrating this little function to get this area here. And that would be the probability of a bullseye. But if you took the same relative radial distance, let's say it's 1 or 2 centimeters, but then you did that out over, here, you'd actually get a much taller rectangle, which means you'd have higher probability. Which is reflected when you go actually look at a dartboard, you'll see there are regions where, well, in addition to the bullseye, you've got a region where you get triple the score, which is in a small band around here. And then on the edge here, again, hard, but you get a double score. And so the scoring system is specifically weighted to reflect that. It's easier to hit something near the rim than it is to hit something that's in a band, even concentrated just a little bit in, even if that band has the same width. It's just because area is a function of radius, you're more likely to hit it when it's farther out. Let's do another example that's kind of related. Circular example. So again, we've got our circle here, and I want to imagine picking a point uniformly at random from the circle. So you can think of this as like I have a spinner, and like on a clock, like one of those twister spinners, and I'll say I spin it. And then whatever point it points to is the result of this experiment. So once I do spin it, and I get to some, other value here, that's the result of my experiment, I can ask, well, what happens if, say, I look at the x coordinate of my value here? So said a little more rigorously, I sample a point uniformly at random from the circle, and then I read off the x coordinate. So we're going to record that as a new random variable, capital X. So how is X distributed? Always the question we're trying to answer here. Well, again, we want to try to use the CDF trick here. And so we can kind of see here that at least for positive values of x, and we recognize that negative values of x are, if I try to accumulate the probability that it lands inside of some window, then I can look at, for example, probability that x lands inside of this window. It's going to be the same thing as integrating the probability that x lands inside of these two arcs. So said slightly differently, the probability that capital X, our random variable, is between 0 and little x, indicating the picture, is going to be the area of the two arcs, blue arcs, divided by the total circumference of the circle. And the reason this is true is because our point is sampled uniformly. And whenever I say uniformly, that means that probability, at least in the continuous case, can be computed using relative area or relative volume, depending on the dimension of the problem. And so again, this is the two arcs look like this. All right, and again, we know we can actually compute formulas for that. And I'm going to use a slightly different angle than you might be used to. Recognizing that you can go either way. Let's let this angle here be alpha. Normally we like to measure from the x-axis, but there's nothing to prevent us from measuring from the y-axis. That's usually what we talk about when we use like theta, for example. Remember, this relative area is going to be the thing which we would integrate or find if we go from 0 to x of the PDF of little x prime dx prime. But again, we can find the formula for the other thing more easily. Right, this is what we're trying to find. But if we continue the area calculation above, it's fairly easy to see that this is actually, arc length. If we're measuring in radians and we're looking at a unit circle, this is going to be 2 times the arc length of a single blue arc divided by the circumference, which we know is 2 pi. So writing out the formulas for it, it's 2 alpha over 2 pi. So we actually end up getting alpha over pi. Now, how do we find alpha in terms of x? Because again, we want to relate this answer somehow to x again. Well, we know we can find alpha in terms of what's called the arc sine of x, which is sometimes also written as sine inverse of x. But I want to caution you that this is not the same thing as 1 over sine of x. It's the inverse function to sine, because in this case, if you think about it, if I look using maybe the slightly darker gray, and I think about this triangle here, this ends up being my x value. And you can see that it's now the opposite over the hypotenuse when measured with respect to alpha. So this is the same thing as 1 over pi inverse sine of x. And so we've now found the CDF. This is the CDF. And so again, just by applying the derivative, we can then say that, well, d dx of 1 over pi arc sine of x, which is 1 over pi square root of 1 minus x squared. This is our PDF. And so we are now done with this problem. So again, it seems like such an innocent question. You know, I find a random angle, and I read off the x value. How are things? What's the distribution of the x values? And again, it seems really straightforward, but suddenly you have to bring in all this trigonometry and stuff from pre-calc, which maybe haven't used in a bit. And you end up having to remember things like, oh, what is the derivative of inverse sine or arc sine? And that, well, you know, now it turns out to emerge very naturally in this problem. It's not just something that's completely contrived. We'll talk a little bit more about this, but you know, I want to note one thing, which is that you know, how is this distributed? Well, it kind of has this. So what is the graph of the PDF for x? So again, we've got maybe values from -1 and 1, assuming we're looking at a circle with unit radius. So now these are our x values. And I want to graph what's the probability density. I have this 1 over pi square root of 1 minus x squared. Well, so if we think about, well, what happens when we plug in x equals 1? Well, at x equals 1, this ends up being 1 over pi. Oops, I don't need that last one. This is 1 over pi at x equals 1, or x equals 0, sorry. But what about what happens at x equals, let's say, a half? Well, if we just plug it in, we get a fourth. And so then we're looking at 1 over pi 1 minus a fourth, which is 3/4. And you know, let's just go ahead and get an exact value for that. So 1 divided by pi times square root of 3/4. So ends up equaling all right, 0.367. If we compare that with, you know, the value of just 1 over pi, which is about 0.31, we see that it's increasing. And indeed, as x approaches plus or minus 1, we're going to get closer and closer to dividing by 0. And so the graph of this now looks something like and it reaches these sort of vertical asymptotes at plus and minus 1. I'll leave that to you to think about how you might interpret that. And why does that make sense that when I pick a point and I read off its x values, how does this sort of push forward of the probability from up here, how does that sort of pile up? And I think maybe you can see sort of intuitively what's happening is as you approach that end of the circle, the sort of tilt here means that more and more area is being concentrated into smaller and smaller values of x. So actually the density does get sort of infinitely large as we approach there. And this has to deal with the fact that, the sort of slope of this line is becoming increasingly vertical, which means its slope is becoming increasingly steep, increasingly infinite. So the question you want to ask yourself is, why does this make sense? X approaches plus or minus 1. And I want you to kind of consider that cartoon there. Let's go ahead and do another example, which sort of produces a similar behavior, and it's a fun thing to consider. But before we do that, I want to maybe go back to applying the formula that we introduced at the end of lecture last time, just so we can kind of turn things down a notch. Actually, no, it makes most sense for me to go ahead and address this now. So here's another situation in which this so it depends on how good I am at actually vibrating this pencil. But so here I've got my Apple Pencil here, and I want to sort of start wiggling it in front of you. All right, so hopefully you're looking at my camera here, and you can sort of see that it has this, it almost starts to look like rubber, even though Now the question you want to ask yourself is, why does it look like rubber? Even though this is a very hard pencil, I can not made out of rubber. Or if it is, it's stiff. I definitely can't bend it. But when I wiggle it and I kind of get into this nice forcing regime, you get this sort of rubber-like appearance. So this is sometimes called the rubber pencil. And the essential setup here is, you've got so you've got your pencil here, and you've got the eraser here on the end. And so what you can do is you can take your little fingers here and all right, right, so this is my claw-like hand. And you can just imagine moving up and down. And what ends up happening is if you trace out sort of the arc of where this pencil goes to, you can see that the spectrum of possibilities tends to concentrate around these two endpoints here. So what you observe here is that these sort of turnaround points. And what's happening is that those turnaround points, just like when you throw a ball up in the air and it finally reaches the apex of its trajectory and then comes back down, what's happening is it's reversing velocity from, say, positive velocity measured from the Earth to the negative velocity. And so that means, just by our normal, Rolle's theorem or whatever, there is some point where the velocity is zero, which means there's also at these turnaround points, that's when the pen is at zero velocity. And of course, you can just see things if they're not moving. So you tend to actually, when your brain is sampling frames per second, you're actually seeing it mostly here and here. But that sort of extreme is happening at different locations based on the geometry of this pencil. And so consequently, you get this weird state where you see it mostly here and here, but it's more likely to be here versus over here. So then your brain kind of stitches in this set of turnaround points, and it creates this weird sort of rubber appearance. So the question is, how do you model this? So you can model the eraser location and time. And I'm going to think of its by location, I mean here, its y position as a function of time. Using what's called a simple harmonic oscillator, SHO, which just means that y of t looks something like y0 times sine of t. So if you think about, so imagine you're equally likely to observe the pencil at some time t, which is, say, uniformly distributed, and just for the sake of making the math simple here, I'm just going to say we set time to be at 0.0, which is sort of proportional to the angle. So the bottom line is, like, your observations in time are sort of uniformly distributed, but now you're looking at a phenomenon whose position is a function of time. All right. So now the question is, what is the PDF for y, which is this function y0 sine of capital T. So I'm going to go ahead and just use a formula instead of going through the CDF trick. We can just look at this formula. So let me go ahead and say here we have this useful formula. And this is a slight variation on something we did at the end of last lecture. And so let me just write it down here. So let x be a random variable and g a differentiable function that is one-to-one its domain. What this equivalently means is that there's a unique inverse, which also you can think of as passing the counterpart to the function test, which is the horizontal line test. Passes the horizontal line test. So this is injective, also called one-to-one, but this is not. So this is a green arrow. This is a red X. It's not one-to-one. All right. So assuming you've got a differentiable function that's one-to-one on its domain, and we think of this domain as being the support. This is the place where f of x, little x, is not equal to 0. Then the PDF for y is left little y. So we need to use the PDF for x, and we're going to be evaluating it at the inverse of y, which is unique because we have a one-to-one function. And then we're multiplying this by 1 over the absolute value of the derivative of g evaluated at that same point. So I think this is the derivative of g. And this is the inverse of y under g. Now, if you recall, we had back in the last lecture a summation formula in front of this, which essentially says we can drop this one-to-one assumption by then instead summing over all possible pre-images or inverse images. These are basically inverses of y. But there, in this setting, we can get around this requirement a little more easily. So returning to the example. Oops. So now I want to just apply it. So one way to think about it, so we know that g of t is equal to y0 sine of t. We need to, so let's just go ahead and graph what this function looks like. And we know that we're looking at t supported from minus pi over 2 to pi over 2. And so if we do that, you think about what the graph looks like here. We see this is a function that does actually pass this horizontal line test. So we can actually find the distribution on y just by sort of pushing forward the distribution on x. So the pipeline is going to be something like this. So we've got, this is the distribution for t. And now we're applying our function and then pushing back down onto the y-axis to get our distribution on y. So this is going to be the support for f of y, of little y. So we can now just apply this formula. So just to go back real quick. So we've got g, we need to figure out what inverse g is. We know what x is, it just ends up being uniform. Although let's double check and make sure we understand what is f of x here. So here we think of x as equal to t, which is uniform on minus pi over 2 to pi over 2. Right, so I guess I should have made this closed. So what does that mean? It means that f of t has to be 1 over this length, which is pi. So that's our f of t function. Of course, this is for when t is in this region, and then it's going to, of course, be 0 otherwise. Now we just need to figure out what is g inverse and what is the derivative of g. So let's just go ahead and figure out what is the derivative of g. So we know that the derivative of g, well, derivative of sine is cosine, right? And we can see that starts off as positive 1, and then it sort of flattens out and approaches 0 as we get to pi over 2. So this looks like y0 cosine of t. And so now we're pretty much ready to apply the formula. So f of y of little y is going to equal, well, let's just go ahead and look at it again. So it's f of x, that's t, f of t of g inverse of y, and then divided by this derivative. So it's going to be f of t evaluated at g inverse of y times 1 over g prime, which will be y0 cosine of t. But now we need to convert this. Well, I guess this is the same thing as g inverse of y. Sorry. All this is telling you is what's the point in time that that we end up getting that value t, g inverse of y. And that's actually relatively easy to solve. So remember, so y equals y naught over sine over t. So this implies that y over y0 equals sine of t, which tells you that t is equal to the inverse sine of y over y0. So we can just effectively think of this as t. And so we now actually have sort of figured out what this guy looks like. But we want to eventually re-express everything back in terms of t. Now again, luckily f of t is just going to be 1 over pi. Is going to be 1 over pi for t inside of, minus pi over 2 over 2. So that part's easy. But now we need to figure out what is this this derivative as a function of y. So in order to figure out the derivative as a function out of y, so just to write it down, what do we know so far? We know f of y of t is 1 over y naught cosine t. But we need as a function of y. So let's just go ahead and run through that a little bit here. So we need to express cosine of t, 1 over cosine of t in terms of y. Well, we know that cosine of t is equal to the same thing as square root of 1 minus sine squared of t. This just comes from the fact that sine squared plus cosine, sine squared plus cosine squared is equal to 1. So then in particular, if I plug this in, I now have f of y equals 1 over pi y0. Cosine is the same thing as square root of 1 minus sine squared of t. But then I need to realize that this sine of t squared, just to make the notation a little bit clearer, is going to be sine of inverse sine of y over y0 squared. So then the final formula is we end up getting 1 over pi. And because square root's always going to be defined as positive, I can drop the absolute value. This could be 1 minus y over y naught squared. Oops. Which again looks exactly like this this thing where we see probability concentrates here. Oops. Probability density. And so we've just empirically proved that even if your sampling rate is uniform in time, when you look at this pencil, you tend to see it concentrated at the endpoints. And then your brain's process of trying to stitch together these frames is creating this illusion of your pencil sort of becoming rubber, or at least some people claim it does. All right, so I wanted to keep today short, and then in class during the worksheets, we're gonna practice using this formula that I introduced here. All right, so I look forward to seeing you in class soon.